Hi guys, welcome back to Statistics. This is Mr. Robeson. We are still looking at probability today. So we're going to look at some myths about probability. We're going to talk about what a sample space is. And we're going to take a look at complement and addition rule, which we kind of looked at the last presentation as well. All right, so we have something called the law of large numbers that says if we observe more and more repetitions of any chance process, like flipping a coin, say that's happening here, the proportion of times that a specific outcome occurs approaches a single value. And that single value, the proportion of times it occurs, is going to be the probability that it occurs. For instance, like we're flipping a coin. So we got the first one was heads, the second one looks like was tails. So that means 50% of the time it's heads. Then we got another heads, and we got another tails. So again, 2 out of 4 was heads. All right, and we just kept doing that back and forth and over and over and over again. And what it says is if we do this many times, like 500 times, that proportion is going to approach the actual probability of that thing happening. All right, so that's another way we can look at defining probability. It's the proportion of time something would happen in the long run. So if we were doing something in the real world. All right, so how would this apply to our Skittle experiment? Well, with our Skittles, we said that it should be, each one should be 1/5. Like the proportion, my color is red, so it looks like I'll talk about red. Proportion of red Skittles should be 1/5. But what we got in our bag, it wasn't 1/5. I don't remember what it was, but it was not 1/5. All right, but what that says is if we do this repeatedly, so if we took many bags of Skittles, and we put them all together into one giant bowl of Skittles, the proportion of red would approach 1/5. All right, the bigger our sample size, the more likely it is to get to the actual proportion, the actual probability, when we're doing examples in real world type things. All right, so some myths about randomness. So people get tricked up on these all the time. So the idea of probability is that randomness is predictable in the long run, all right, but not in the short run. All right, so if we just looked at that one bag of Skittles and we want to say 1/5 of them are going to be red, almost 100% of the time we're going to be wrong about that. But if we put more and more bags of Skittles together, in the long run, we'd be likelier to be right. All right, so that's what it means in our Skittle experiment. All right, what about the law of averages? So probability tells us random behavior evens out in the long run. However, future outcomes are not affected by the past behavior. That is, past outcomes do not influence the likelihood of individual outcomes occurring in the future. All right, so now the way this would work with our Skittles, it wouldn't necessarily be true for one bag, but if we took like 100 bags of Skittles and poured them into a giant bowl, and we picked out one Skittle and it happened to be red, the probability that we're going to get red on the next draw is still going to be about 1/5. So it's not going to change. The probability is still going to stay the same the next time we do it. Even if we reached into that bowl maybe 5 times in a row and picked out red, the chances of us getting a red Skittle the next time is still going to be about 1/5 because that bowl is so big. So past outcomes are not going to affect future outcomes. All right, so here's an example. Suppose you flipped a fair coin and got 5 heads in a row. What is the most likely outcome of the next coin flip? So remember, this is a fair coin. So if we flip a coin again, and we haven't talked about this much, but we did have it on the last couple of slides back. The probability of heads when you flip a coin is always 1/2. And the probability of tails when we flip a coin in this class is always going to be 1/2, unless said otherwise. Fair, that means 1/2, 1/2. So if we got 5 heads in a row, next time you flip the coin, what's going to happen? Well, it could be heads, could be tails. Both are equally likely. Maybe the coin will land on its side. Who knows? It won't. All right, so what ends up happening is both of them are still going to be 1/2. So we're still going to be 1/2, so they're both still going to be equally likely. All right, so next up, when we're talking about our probability model, sometimes we talk about our sample size, sometimes we talk about our sample space. So sample space, I haven't seen it come up on the AP exam, but it's all possible outcomes. So it's what the outcomes are. It's not how many things that can happen, it's just what the outcomes are. All right, it's like what values your variable can take. Right, the probability model is a description of some chance process that consists of two parts, a sample space S and a probability for each outcome. So in other words, for the sample space for flipping a coin, S would be heads and tails. And then we'd have a probability of heads equal to 1/2 and a probability of tails equal to 1/2. So this is our sample space over here, and this would be our probability model, what could happen with those probabilities. All right, so if we were going to roll two 6-sided die, what would be the sample space? What could we get if we rolled 2 dice? Well, I could get 1 and 1. I could get 1 and 2. I could get 2 and 1. I could keep doing this over and over and over again, and I could get a whole bunch of different things. In fact, I could get 36 different outcomes. So my orange die here is the first one. I guess that's light green die here is the second one. And it tells us all the different outcomes. So like, say the light green one, we've got 1 6 times in a row, but the orange one goes 1 through 6. All right, and if we go across, the green one, well, no, the white one's going to, or the orange one is going to stay 1, and the green one's going to go 1 through 6. So if we go throughout this entire matrix or table or whatever, we end up with 36 total outcomes in our sample space if we're rolling 2 die. All right, what if we were going to add up the 2 die? All right, now our sample space would change. Our sample space would no longer be all these different outcomes. It would be, so we could add 1 and 1, we could get 2. If we add 1 and 2, we get 3. If we add 1 and 2, we get 3 again. I'm not going to write it again because we already got it. But we could get 4. We could get 5, 6, 7, 8, 9. We can keep going all the way until we get to this last one, which would be 12. So we can get anything from 2 to 12. That would be our sample space S. So those are all of our possible outcomes. So it's got, looks like 10 possible outcomes there. All right, so some properties. So we kind of looked at these last time, and we said that complement probability. So the probability that event A does not occur, all right, is 1 minus the probability of A. All right, now why this works is because if we add up all possible probabilities, so if we add up all the probabilities in the sample space, where X is in the sample, I'm using notation, you don't know, it's okay. But if we add up all the probabilities of all the variables in the sample space, we should get 1. All right, so if we take one particular event in the sample space, call it event A, maybe it's just, adding up to get a 2, or maybe it's adding up to get 4 or less when you roll 2 die. It would be 1 minus the probability of that event, would be the probability of it not happening. All right, that's how complement probability works, because the probability of A plus the probability of not A, which would be everything else, is going to add up to 1. So if we want to solve for the probability of not A, probability of not A would just be 1 minus the probability of A. All right. If we have 2 events that have no outcomes in common, then the probability of one or the other is the sum of their probabilities. So if we want the probability of A or B, well, that's the probability of A plus the probability of B, as long as they don't have anything in common. All right, so when things don't have anything in common, we do have a fancy word for it. It's called mutually exclusive, or we can call it disjoint. So we have 2 fancy words for it, really. If they have no outcomes in common, in other words, the probability of both things happening at once would be 0. All right, so in other words, like what would be the probability of getting a red Skittle and a yellow Skittle at the same time? Well, if you're going to grab just one Skittle, it's going to be 0. They have no outcomes in common. But if we wanted the probability of red or yellow, well, we would add up their 2 probabilities. All right, so the probability of red is 16 out of 60. Probability of yellow is 12 out of 60. So we would get 28 out of 60. You could also add up the 16 and the 12 first and then put it out of 60. That would work too. All right, what about the complement probability? What about the probability of not getting yellow? All right, well, the probability of not yellow will equal 1 minus the probability of yellow. All right. This is like the 60 out of 60 that we had. We can still just call it 1, but this is 12 out of 60. So it's telling us how many Skittles are left over here. So the 60 out of 60 minus the 12 out of 60 gives us the 16, the 8, the 14, and the 10. In other words, it will give us 48 out of 60. So that's how complement probability works. All right, so the probability of flipping a fair coin and getting heads 4 times out of 4 flips. So that means heads, 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 and a heads is 1 out of 16. So the probability of 4 H's is 1 out of 16. What is the probability of getting at least 1 tail out of 4 flips? Well, how is the probability of 4 heads and at least 1 tail related? Well, so either when we flip it, we could get, if we're flipping it 4 times, we could get head all 4 times, like heads, 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 or we could get heads, 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 tails, heads, heads, tails, heads, heads, tails, heads, heads, tails, heads, heads, heads. So that's all the ones with 1 tail. We could also say get 2 tails. And there's some more of those. We could get 3 tails. There's some more of those. We could get all 4 of them are tails. Oops. All right. Now the question is, how many total outcomes are there? Well, we don't actually need to know, because we have this one is 1 in 16, which might tell us there's 16 total outcomes. But this would probability of not 4 heads. All right. The probability of not 4 heads, those two should add up to 1. Probability of not 4 heads is the same thing as the probability of at least 1 tail, because all of these have at least 1 tail. This one has 2, these ones have 3, this one has all 4 tails, so all of them have at least 1 tail. So these two are complements. That means the probability of at least 1 tail is equal to 1 minus the probability that all 4 are heads. And we already know that probability. 1 minus 1/16. So we get 15 out of 16. All right, if that seemed tricky, it's okay. We're going to do some more at least 1 problems in another presentation. We'll do a whole set of them. All right. They do like those on the AP exam, though. They are about 50% of the time. All right, so 15 out of 16. All right, back to easier stuff. So there were 55 Skittles in a bag of Skittles. If those Skittles, of those Skittles, 12 were red. So we had 12 red Skittles, 10 were green. What is the probability of getting a red or a green Skittle if you randomly choose one from the bag? Well, probability of red or green is equal to the probability of red plus the probability of green, since there is no overlap between them. Probability of red is 12 out of 55. The probability of green is 10 out of 55. All right, we already have a common denominator. 12 plus 10 is 22 out of 55. There's our answer. All right, so that's it for that. So we looked at complement probabilities. We looked at the addition rule. That's when we're working with OR. And we looked at what the sample space is, all the possible outcomes. Next time, we'll get a little more complicated with conditional probability.